So just sort of to give you a bit of a feel for what we're dealing with in the synthesis report, which is the 7th report in the IPCC cycle. So there was 3 previous special reports, the 1.5 degrees report, the land report, and the oceans report. Then there was the Working Group 1 report on climate science, the Working Group 2 report on impacts and adaptation, and Working Group 3 report on emission reduction. And this synthesis report pulls information across all of those 6 other reports into a relatively concise sort of summary, which nevertheless is approved word by word and line by line by the IPCC plenary, so the governments of the world. So this is a shared document between the science community and the policymakers across the world. So the numbers associated with this, there was 93 people involved in the writing of this synthesis report, and also the editing, review editors of that. These people came from 43 different countries. The gender and country splits of 40% developing and 60% developed countries. So there's a bit of work needed to be done to balance that out in the future. And in terms of gender, 44% women and 56% men, again, need some balancing out in the future. Just in this last version of this, there was about 7,000 review comments. In many of these reports, we get things like 30, 40, 50,000 comments on a report. So there's a huge amount of review of these documents. And in fact, I sometimes say that these are probably the most documents, the most reviewed documents in the history of humankind, when you actually look at the multiple stages of review and the intensity of that review. And this synthesis report synthesized around about 12,500 pages from the other reports, each of which page is dense text. So if we look at the really critical sort of messages coming across this report, so obviously temperatures and temperature change is one of those. But importantly, one of the messages coming across this report and the previous reports in this cycle was messages about equity. And so that's one of the things I want to highlight in this short presentation. So what these set of graphs show is the change in the hottest day each year under different temperatures. So 1.5 degrees, 2 degrees, 3 degrees, or 4. Hopefully we're not any longer on the 4-degree trajectory. We've started to steady our emissions sources, not reduce them yet, but at least sort of cap them a little bit. And so at the moment, we're probably heading towards a 3-degree world. But the goal is, the Paris Agreement goal is to head to a 1.5 or 2-degree world. That's what the Paris Agreement is. And we can see that what the world looks like under those different temperature scenarios, going from 1.5 degrees up to 4 degrees in this graphic. Now, really importantly, associated with that equity sort of element there, is that different places warm at different rates. So if you're in the middle of a continent, you warm up faster than at the coast. If you're on a continental landmass, you warm up faster than the oceans. If you're up the northern end of the continent, the globe, or the southern end, so the Arctic or Antarctic, you warm up faster than most of the equatorial zones. So there's a geographical equity sort of element, which I'll emphasize throughout this short talk. And it tends to be that people who are in developing countries tend to get the raw end of the deal in terms of climate change. So often they're the ones who've actually contributed least to the climate. If we look at things like rainfall intensity, which generates things like flash floods and erosion in farming lands and similar things, that's also likely to increase with global temperatures. So the same sort of scenario of different temperatures here, 1 to 1.5 degrees up to 4 degrees. And you can see that as we increase temperatures across the globe, we also increase rainfall intensity. So the flood risk increases at the same time across many parts of the world. And in fact, these assessments may well underestimate increase in flood risk. So for example, in Australia, we're anticipating, around about 3 degrees, something like a 10 to 15% increase in flood risk or rainfall intensity. But what we've already experienced in the Sydney Basin over the last 2 decades is a 40% increase in rainfall intensity. So it was a study using rain radars as a way of measuring rainfall intensity. So in many ways, some of these scenarios are underestimates of the potential rates of change and degree of change. And if we look at things like temperatures under different scenarios in a slightly different way, what this shows is the different colors going from blue up to dark reds indicate the temperature increase above pre-industrial. And what this particular graph shows is different emission trajectories ranging from the very high to the very low result in quite different temperature trajectories and temperature results. But in particular, what this graph shows is what this means on an intergenerational scale. So I mentioned equity before, and there's issues of geographical equity come out, developed versus developing. But in this report, we also talk about intergenerational equity. And in particular, what this graph shows is that the world that people of, say, my generation experienced will be very, very different from the world that my children or my grandchildren experience. And in fact, other studies have shown that a child born today will experience 3 to 4 times on average more extreme events than their grandparents. And in some parts of the world, that's up to 17 times more than their grandparents. So for people born today, what used to be an unusual event, twice in a lifetime, could well become a once in a decade event for people who are born today. So there's a strong intergenerational consequence of climate change as well. And we see very, very uneven distribution across different systems. So if we're looking at the top set of graphs, which again go from, on the left-hand little panel, that's the historical frequency of heat stress at the top left, and that shows the number of days different heat stress days occurred. So heat stress is where a combination of high temperature and humidity make it problematic for a human to go out and do anything more than light exercise outside. If you do more than that, your interior body heat builds up and you either get heat sick or in some cases heat stroke and possibly even death in that circumstance if you don't manage it. And what we can see from those graphs up the top is as we go up towards 2 and 3 and 4 degrees, many parts of the world effectively have every day becoming a heat stress day. And so really, really significant challenges in terms of health, in terms of productivity, in terms of agriculture, buildings, infrastructure, etc., as a result of increased risk of heat stress days. And it's not just things like heat stress that get affected, but also things like fisheries. So the bottom 2 graphs here show changes in fishery productivity under a sort of a 1.5 degree scenario on the left and about a 4 degree scenario on the right. And you can see that all those purpley colors are all big reductions in fishery productivity. And in fact, again, you can see a very strong geographical inequity where if you're up in, say, Europe, parts of Europe and around the Arctic may actually get increases in productivity. But if you're around the equatorial and subtropical regions, you actually get very significant decreases in productivity. And importantly, in many parts of the world, in these areas, fish protein is a core source of protein, a core source of nutrients for people and their diets. So we can see many different types of impacts. Now, one of the really important impacts for us and also for our neighbours in the Pacific is what will happen to sea level rise. So this is just picking up the key threads from the Working Group 1 report and the Oceans report. And it shows, again, different emission scenarios, the very high to the very low emission scenarios, roughly equivalent to a 5 degree increase in temperature or a 1.5 degree increase in temperature. And they have very different implications for sea level rise, even up to the end of this century. So if we go on a very low emission scenario or 1.5 degrees emission scenario, we may be able to restrict sea level rise to 0.5 metre. But if we go on a high emission scenario, by the end of the century, it will be much more like 1 metre. And importantly, the IPCC could not rule out much higher sort of scenarios of sea level rise by the end of the century, including up to about 1 3/4 metres. That's by taking into account a lot of the processes like ice sheet breakdown, which are now observed but are not yet incorporated into the simulation models. Now, importantly, sea level rise is a long, slow burn sort of issue, is that we're already committed ourselves to centuries of sea level rise from past greenhouse gas emissions. And the sort of panels on the right-hand side indicate what might happen to sea level rise by the year 2150, and then on the right-hand side, 2300. And we can see that essentially sea level rise will keep on going up to year 2300 and subsequent to that. And these levels of sea level rise are, things like on a high emission scenario are things like, 2 to 6 or 7 or more meters of sea level rise. So more than enough to swamp many low-lying Pacific atolls and many other low-lying parts of the world, such as around Indonesia and Thailand and China and Bangladesh, etc. So very big concerns there. Now, moving on to what we call risk assessments is moving beyond just the impacts of climate change, the changes in temperature, etc., into what it means for different systems. Every IPCC report, we produce what we call burning embers diagrams. These are essentially risk diagrams. So the temperature increases on the vertical axis of these colored diagrams, going from sort of no change up to 5 degrees. And the color intuitively indicates the level of impact or risk that different systems experience. So the fatter bars are what we assessed in this assessment, the 6th assessment cycle, and the thinner bars on the partner bar is what we measured or assessed in the 5th assessment cycle, the previous one. And what we see right across these different systems, and I'll describe them in a second, that in every case, we are assessing a higher level of risk, of consequence at a given temperature this cycle compared with the last cycle. So the more we know about climate change, the more we get concerned about it, the higher the level of risk is at a given temperature. And when we do this, we traditionally sort of separated this into 5 aggregate systems. So the pair of bars on the left is the biodiversity risk. Then there's a risk from extreme weather events, risk from equity issues and distribution of impacts. There's a global aggregate impact risk on things like food security. And there's what we call large-scale singular events. That's like the shutdown of the Atlantic conveyor circulation system, the sort of day after tomorrow scenario. And across all of those different systems, you can see that at any given temperature, our current assessed risk is greater than the previous assessment. And in fact, just a few assessments ago, we had to add an extra color into these assessments because things were getting more and more problematic than we anticipated. So we had to introduce that sort of purpley crimson color, which indicates irreversible, unmanageable, and large-scale risk. So we're seeing more and more of that across these different systems. Now, importantly, these risks vary significantly across different systems. So tropical coral reefs are much more risk than, say, food security. And so different systems have different levels of risk at a given temperature. And of course, we can adapt to these changes and reduce the risk at a given temperature. So these bars are typically largely unadapted systems. And really importantly, this report shows us a way ahead. It doesn't talk about the problems, it talks about the solutions. It talks about our reasons for concern, but also our reasons for hope that we can actually deal with this effectively. And those reasons for hope, the points of action, are twofold. One is we can adapt to climate change, the changes we're already seeing and the changes that are coming down the railway track at us. And we can also reduce our emissions. And so we can avoid the worst of climate change by reducing our emissions. This particular graph has both of those elements in it, an adaptation element and an emission reduction element on the left-hand side and the right-hand side, respectively. Now, I'm going to zoom in on this a little bit so we can read it, but importantly, what this is sort of lined up as is in different systems. So we have on the left-hand side, we've got energy systems, land, water, and food systems, settlements in infrastructure, health, and sort of broader societal well-being sort of issues. And each of them have multiple sort of points of adaptation and multiple points of emission reduction. And just focusing on the left-hand bars, the ones with the sort of bluey-grey rectangles and the dots, we can see if we zoom in, say, into this case, the land and water systems, we can see there's different sets of adaptations which are listed here. Things like biodiversity management, sustainable aquaculture, integrated coastal zone management, etc. And against each of those is assessed the potential feasibility, with the darker rectangles being more feasible, and the confidence in that assessment, which is the number of dots. So if there's 3 dots, it's very confident that we have feasible options. And then the next row of rectangles is the synergies with emission reduction. So are these adaptation responses congruent with emission reduction activities, or are they in opposition with emission reduction activities? And so where they're dark blue, there's a lot of congruence. There's a lot of synergies between the adaptation task and the emission reduction task. And importantly, what this report shows in terms of adaptation is, whilst adaptation is a good news story, it's our way of managing change, there are big possible issues with it at the moment. So what this report shows is that despite progress in terms of adaptation, where we're seeing different people and different systems adapt, adaptation gaps still exist. So the difference between where we are in terms of adaptation and where we rationally should be in terms of adaptation is large, and it's also growing. So we anticipate that gap is going to grow over time, and that gap will be largest amongst poor people and least amongst the wealthy. So there's an equity issue coming out there. We also note that most observed adaptation happening across the globe is fragmented. It's very incremental in nature, so it's tweaking existing systems. It's often very sector specific, and it's unequally distributed regionally. So we get some places are adapting more than others. And often that's again lined up with developed versus developing countries. We also observe that there are lots and lots of barriers to effective adaptation. So there's lots of reasons why it doesn't happen. But we also observe we broadly know how to overcome those barriers. It's just that we're not doing that at the moment. We note that adaptation options which are feasible and effective today, so the things which can manage small amounts of climate change or relatively small, will become more constrained and less effective with increasing climate change. So our ability to manage future risk actually declines with increased temperature increase. So even though we might think we've got good adaptations today, they're likely to be less and less effective over time. And lastly, the point that I made in the previous slide is that many effective adaptation responses can also reduce greenhouse gas emissions and also enhance sustainable development. And in fact, one of the key messages, aggregate messages from this report, is you can't have effective climate response without sustainable development, and you can't have sustainable development without an effective climate response. Now, just in the last part of the talk, the last few slides is about emission reduction. So obviously this is, a lot of attention being paid by people like Chris Bowen on this. But what this report says is that we need deep and sustained and rapid emission reductions, much more than we currently are doing. So unfortunately, when we look at the current implemented policies around the globe, that will lead us to a temperature increase of something like about 3.2 degrees. So we're not really on top of the climate change issue here. To actually get to 1.5 to 2 degrees, which is what we've committed Australia to do as part of the Paris Agreement, we have to go on that green or that sort of bluey set of lines down the bottom. We have to reduce our emissions much more quickly than we currently are doing, and more quickly than is outlined in our current national policy, 43% reduction by 2030 against 2005 levels. So we need to do a lot more in terms of emission reduction than we're currently doing. If we look at another way of looking at this, which is what we call the emissions budget, the carbon budget approach, we can sort of do the numbers about how much more emissions we can emit and still stay within any given temperature target. And that's because there's largely a linear relationship between accumulated carbon dioxide emissions and temperature. So it's the accumulated emissions, not the year-by-year emissions, but the emissions since the start of the pre-industrial period added up over time is linearly related to temperature increase. And that's because carbon dioxide hangs around for a long time in the atmosphere. Now, the important messages coming out of here is that effectively we've got a very constrained carbon budget that's consistent with 1.5 degrees. So less than 500 billion tonnes of carbon dioxide to emit. And unfortunately, just our existing fossil fuel infrastructure, coal-fired power stations, etc., across the globe will completely chew up that 1.5 degrees emission budget by themselves, without including transport or agriculture or industry or waste. Just our existing fossil fuel systems by themselves, if they live to their end of life, current planned end of life, will chew up the entire emissions budget that's consistent with 1.5 degrees. And if we look at the existing and planned fossil fuel emissions, so this is planned gas-fired power stations, etc., that will almost chew up the budget by itself that's consistent with 2 degrees. And this is why the IPCC and the International Energy Agency and others say that if we're serious about emission reductions and temperature goals, we can't have more coal and we can't have more gas. We have to not only stop opening up new ones, but we have to close down the existing ones if we're to meet those temperature goals. And importantly, again, if we look at the right-hand side of this graph, the one with the pretty colored bars, these are all different emission reduction options. So at the top, we've got things like solar and wind. They're the ones which the size of the bar is the potential emission reductions associated with each option. And the color of the bar indicates the profitability, the economics of that. So if it's a blue color, you can either do that either at a profit or at a very low cost. Once you get to the orangey colors, you can do that, but it actually costs you a fair bit of money. So you can see right across this right-hand graph, there's lots and lots of blue columns. There's lots of options to reduce our greenhouse gas emissions at very low or negative cost. So it's not as though we haven't got the things to do that can actually reduce our greenhouse gas footprint. And if we just zoom in on this, in this case, just looking at settlements and infrastructure. So if we look at the right-hand columns, we can see that fuel-efficient vehicles can be implemented fairly easily in terms of dollars, but it only can take out about 1 of 50 gigatons of carbon dioxide and greenhouse gas emissions in any given year. So it's only going to be a part of the solution, a small part. And similarly, efficient lighting and efficient shipping and aviation can all be done relatively profitably, and they all take a small chunk of the pie out, but we're left with big chunks of the pie remaining. But if we actually aggregate all of the possible options there, what this report shows is potential demand side reductions. So those are things like reducing our, moving to electrified buildings rather than gas-fired heaters and things like that, is that we could actually reduce our emissions very substantially. So we could reduce emissions by 3/4 through effective electrification of our systems. We can reduce our transport emissions by about 2/3, our building emissions by about 2/3, our food by a bit less than half, and our industry by 1/3, just with the emission options that are available right now. And so again, there's a whole series of barriers to actually why people aren't doing that and why industry isn't doing that and why governments aren't doing that. But by and large, we know how to overcome those barriers. And a lot of it is to do with finance. And just following up, the last point I want to make in this presentation is when we actually pull together all of this information across the different IPCC reports, it's very clear that the global benefit of climate action is much, much greater than the cost. So even just the economics of removing our fossil fueled infrastructure is actually paid for by the reduction in the illness and mortality of people who are affected by air pollution, let alone the benefits that can flow from reducing future impacts in terms of flooding and sea level rise and all of those sorts of things. And when you add up all of those things, the expected benefit of decarbonisation is really massive compared with the cost of decarbonisation. So I think that's a really important point. The economics is very clear. that action on climate change pays, and it pays big time. So I'll just leave it there for today.